Happy to have Camillo De Lellis from the Institute for Advanced Study, and he will talk on locally dissipative solutions of the Euler equation. So, Camillo, welcome.
Thank you very much. It's a great pleasure to talk in honor of the 75th birthday of Sasha. The first time I heard about him, I was a very young PhD student, and I was very impressed by the fact that he was mentioned by a friend who's not working at all at anything which is related to what Sasha is doing. But he was just pointing out to me about this amazing mathematician who has such wonderful originality in whatever he's doing, and he mentioned he works on the Euler equations, and so that actually attracted my curiosity at the time. And it's also when I it almost marks the first time that I actually got interested in the topic, and since then I've discovered all the beautiful work that he's done, and I'm truly amazed by his original viewpoint in mathematics. Okay, so my talk is going to be about the Euler and maybe a little bit about the Navier-Stokes equations, which I'm actually going to write down immediately. So let me combine them into a single system of partial differential equations, which I will write in the following way. And let me just put a parameter. So V and P are the unknowns, but let me put a real parameter, which I'm going to actually call epsilon, which is bigger or equal than 0, and which is the viscosity of the fluid. And of course, when epsilon is positive, you have the Navier-Stokes equation, and when epsilon is equal to 0, you have the Euler equations. And I'm looking at these equations in the following idealized situation. So I imagine that V is a field which is going from the three-dimensional space times some time interval, which typically I consider to be the whole real line, and it's a vector field. It's giving the velocity of the fluid at the point x and t, and there is the pressure, which is instead a scalar, and of course it's also globally defined, and it's just a map into the real line. And well, for most of my talk, actually, I will be considering objects which are perfectly smooth, even though I will not be solving exactly these equations. But otherwise, there will be, I mean, otherwise, just for the experts, I mean, the others could actually just ignore this remark for the moment. You can interpret perfectly well the solutions in the sense of distributions if you have just something which is square summable. So let me just make the following remark. So if V is in L2, then you can actually multiply components of V with itself. That gives you an L1 function. And then you can just take derivatives in the sense of distributions and understand these equations in the sense of distributions. And P is just going to be it's entering only linearly in the equation, so it's just going to be a distribution. Okay, so now I will be interested in solving most of the times the Cauchy problem. And when I'm solving the Cauchy problem, it means that I'm actually assuming that there is an initial value problem for the fluid. So I assume that at time 0, the velocity takes a certain initial data, which I will call V0. Okay. And one thing which will be fundamental for the rest of the talk is that if you have a smooth solution, then you can scalar multiply. You can scalar multiply the equation, the first equation, by V, and you can carry on some simple computation, and you discover an additional identity, which is nothing but the local conservation law for the kinetic energy of the fluid, for the kinetic energy density of the fluid, which takes the following form. Okay, so here now you're going to have, yeah, let me actually just take this away. And then here you're going to have the Laplacian of modulus of u squared divided by 2. And then you're going to have minus the derivative of u squared. Okay. And of course, if you integrate in space and you assume enough decay, or if you assume, for instance, that you are on the periodic torus, maybe I should have said that in some situation, I might actually want to substitute this domain over here with the periodic torus, just for technical reasons. Then some things actually integrate by parts, and I can derive the conservation law or the law of the dissipation for the total kinetic energy, which is simply the following. So the L2 norm of my solution is actually decaying with a rate which is proportional to the dissipation that you have in your equation, right? Okay, so now I told you that I can actually interpret these equations in a weaker sense if the vector field V is not sufficiently smooth. And famously, there is a result by Scheffer, which was reproved in so this was a result by Scheffer in 1993, which was reproved by Sasha with a completely different method in 1998, I believe. And this amazing result tells you that if you take the minimum amount of regularity to give an interpretation of your system of partial differential equations, then you find something very surprising. You find non-trivial solutions which are in L2, which are square summable, but which are compactly supported in space and time. In particular, being compactly supported in time means that they're equal to 0 for some negative times, maybe, or for some times close to 0. Then at a certain point, they start moving, and then later on, they are identically equal to 0 again. So this is the theorem. So there exists a non-trivial, compactly supported weak solutions. And of course, what is very important now here, what is really surprising in this compactly supported is that they are compactly supported in time too. And that is what makes them actually very remarkable. Okay, and later, Sasha actually proved another remarkable theorem. I believe this was in 2000. So these solutions obviously cannot be energy conservative because the total kinetic energy, this object over here, is equal to 0 at some time, and later on it actually starts being positive. So here we're talking about the Euler equations. So epsilon is equal to 0. And so obviously, if epsilon is equal to 0 and you had a smooth solution, then the total kinetic energy would be conserved, but this is not the case. And in fact, it even violates the principle that the energy should not increase, because at a certain time, the total kinetic energy is equal to 0, and then all of a sudden it actually becomes positive without the action of any external force, because you notice that I just have epsilon Laplacian of V over there, epsilon is equal to 0, but I don't have any F. Okay, and actually Sasha proved in 2000 the first theorem that shows the existence. So there exist weak solutions which dissipate the kinetic energy. And so dissipate the kinetic energy means that really this function over here is strictly decreasing in time. Okay. And I mean, why are we interested actually in these sorts of results? Of course, the first thing that you might simply notice is that this compactly supported solution is some kind of very unexpected thing. So at first, it might look like some sort of curiosity that you know, it's a little bit like, I don't know, the function found by Weierstrass, which is continuous and nowhere differentiable. So people did not expect anything like this to actually happen. And so there is this sort of surprise and mystery, and if you want, monstrosity in it. But when it actually comes to solutions which decrease the kinetic energy, there is a very important motivation which is coming from physics. And the motivation which is coming from physics is usually mentioned in the so-called Kolmogorov's theory of fully developed turbulence. And what this theory is actually telling you is that if you consider a solution a typical solutions of the Navier-Stokes equation with vanishing viscosity, what should actually happen is that even though you have for every positive epsilon solutions which are smooth and which are obeying this law over here, what should typically happen is that the rate of dissipation of the kinetic energy under certain condition should actually be independent of epsilon and should stay bounded away from zero. Okay, so typically for turbulent motions, the total dissipation rate of the kinetic energy should stay bounded away from zero as epsilon goes to zero. So this one should be O of 1, and in particular should not vanish as epsilon goes to zero. So this leads you to then to the obvious expectation that if you take a sequence, a suitable sequence of solutions of the Navier-Stokes equation for this viscosity which is going to zero, the limit can't actually be a conservative solution of the Euler equations. Either it's not going to solve the Euler equation, so it's maybe going to converge weakly, so it's going to behave in a strange way, or else if it's converging to a solution of the Euler equation, then it should converge to a solution of the Euler equation, which is not preserving the kinetic energy, which is dissipating the kinetic energy. And the paper by Sasha in 2000 is actually the first mathematical validation of the fact that such a solution can actually exist. Okay, but in fact, the existence of these solutions was conjectured by Lászlo Székelyhidi in 1949, again in connection with the theory of fully developed turbulence. So the existence of dissipative solutions was in fact conjectured by a theoretical physicist, at least to my knowledge, for the first time in 1949. Okay, and I mean, since then, starting from some works by myself and Lászlo Székelyhidi, there's been a lot of works in which in which, first of all, a connection to what is called the H principle or convex integration in geometry was discovered. And later on, sort of, we started a program to actually prove this conjecture by Lars Onsager, which was proved by Isett. And in general, there's been a series of works in which this program has been actually taken over by younger people and used for other systems of partial differential equations. And what actually convex integration is doing, or what is the N principle is. So there is, say, let me just put it in this way. So there is a very efficient way of producing what you could call unexpected or very irregular, but then not too irregular. For instance, you can produce continuous solutions of not only the Euler equations, but also of several other equations in fluid dynamics. And in fact, let me, for instance, mention one of the surprising things found by Buckmaster and Vicol not too long ago. So in fact, even the Navier-Stokes equation, if you actually relax your concept of solution too much, so even the Navier-Stokes equation have actually distributional solutions, or what are called normally Oseen solution, which can be compactly supported. So even Navier-Stokes has compactly supported in time non-trivial solutions. Okay, so this is like, of course, these kind of very striking and counterintuitive results have permeated into, or have trickled into the literature as like the effect that, by using convex integration, you can construct all sorts of surprising solutions, which are very strange. They are obviously unphysical because, for instance, these solutions of the Navier-Stokes equations obviously wouldn't satisfy the Lidé-Hopf condition on having a control on the dissipation of the energy. And therefore, there's something like very weird. And what I actually want to point out in this talk is that even though this is certainly the case, there is still some genuine understanding of some phenomena that actually this method is in fact achieving. Okay, so this is inspired by some conversation with Sasha. So when we were having some conversation on the way to his home before a dinner, that it was a fantastic experience actually at his place with his wife, he was actually pointing out to me the following, that very much like in his original paper in 1998, what is happening in all of these constructions is in fact that you achieve a strange sort of irregular solution of your systems of equations as a limit of smooth solutions of the same equations with the forcing terms. So let me just point out how it is going on Euler. So in all these theorems, okay, and let me focus on the Euler equations. So the solutions of the Euler equations are obtained as limits of smooth solutions with a forcing term. Okay, so let me actually just focus on the convex integration solutions. So what we are really solving, we're really solving a sequence, for a sequence of solutions of the Euler equations, which this time are nothing mysterious. They are just perfectly valid smooth solutions in which there is, and so, okay, here I will have the divergence condition. And now Q is a natural parameter. But I'm having a right-hand side, and this right-hand side is taking the following form. Is the divergence of a forcing term, which I call R circle Q. And what is this R circle Q? So R circle Q is a smooth matrix field, which is going from R3 times 0 infinity into the space of symmetric 3 times 3 matrices. But it also has the property that the trace is equal to 0. So in fact, in the notation which is usually used in the literature, the reason why there is this circle over here is just to remind us that the trace of that tensor is actually equal to 0. Okay, and they're perfectly smooth solutions. So VQ is C infinity, PQ is C infinity. But what is actually happening is that R circle Q is going to 0 now. It's going to 0 in some weak sense. In fact, in many of the constructions, R circle Q is actually going to 0 uniformly. So not in a bad norm. So it's converging to 0 uniformly, but not too much. I mean, for instance, it's not converging to 0 in C1. So in particular, the fact that you have a divergence over here tells you that the forcing term is going to 0 in a weak sense. And now what is happening is that even though this R circle Q goes to 0, and at all effects, our solutions VQ are converging to a weak solution of the Euler equation, it's as if a part of this force actually survives in the limit. Survives in the limit, and it's the one which is kind of causing, for instance, a dissipation or a change in the kinetic energy. So in other words, when I write down the balance law for the kinetic energy of that object, what I'm actually going to see is I'm going to see something like this. Right, and here I might actually write something like the following. But there's going to be another term which is going to take the following shape. So let me write it in red. And what is actually happening is that, well, this part, which is inside the divergence, is obviously converging to 0. So this is nice, and this is converging to 0. But this thing, which involves the derivative of VQ, is not converging to 0. And the reason is that VQ is converging to a function V, but the derivative typically is actually having a lot of oscillations. So the oscillations of R circle Q, even though they are damped, interact with the oscillation of the derivative of VQ. And that is actually what is creating something which is non-negligible in the limit. Okay, so out of this, you would just conclude that the solutions of the Euler equations that you are creating are in some sense fake, because they are not really solutions of the Euler equations. They're solutions of the Euler equations with a sort of forcing term which has completely disappeared. And this is the point that Sasha was actually telling me in our walk back to his home. But now, when I actually started thinking about it later on, I just thought that he's perfectly right. So this is a very good explanation of what is going on. But in principle, there's actually nothing wrong with that. So this would not be wrong, and nobody would object to this. If this R circle Q were, for instance, the derivative of your solution VQ times an epsilon Q, which is going to 0. Because if I had exactly this structure, then what I would be doing is I would just be considering the Navier-Stokes equations. And what would actually be happening is that I would be having a sequence of solutions to the Navier-Stokes equations with the viscosity, which, yes, it's going to 0. But even though it's going to 0, in this sort of purple term over here would actually interact with the velocity, because there I would just have minus epsilon Q dvq squared and survive in the limit. And so there would be, of course, no objection in saying that this is like, capturing a phenomenon which the theory of turbulence tells us should actually be happening. Okay, and so now I just want to ask the provocative question. And so the provocative question is, how far are we actually? So how far is the R circle Q of the convex integration schemes from the actual thing that you would like to have, which is this epsilon Q dvq, which would actually give you the Navier-Stokes equations. Okay, and of course the answer is that yes, it's in fact pretty far away from that. And but before actually I'm telling you why it's pretty far away from that, let me tell you about some striking things which instead it's captured by this. Okay, so first of all, the first kind of a very simple, naive observation that you might have as a mathematician is that, well, you told me that this R circle Q is symmetric and trace free. Whereas dvq is not, right? Notice, however, that if I consider the divergence of dvq transpose, this is actually equal to the derivative of the divergence of vq, which is equal to 0. So in fact, what I should actually rather be doing in my computation is to substitute this dvq with actually its symmetrized version. And so I should actually add the transpose. And I don't know, maybe divide by 2, but let me forget about that because I can absorb that into a constant. And then I would have something which is symmetric, but not only something which is symmetric, of course, this is going to be trace free because the trace of this tensor is just exactly twice the derivative, twice the divergence of that, right? So the trace of dvq plus dvq transpose is in fact equal to the divergence, and it's equal to 0. So from the structural point of view, actually, we are pretty much there. Okay, so now let us look at another thing. So what is the theory of turbulence telling you? At least qualitatively. Okay, so classically, the theory of turbulence is telling you, and for this, you could, for instance, refer to a famous quote of Richardson, that the way you should understand the fact that there is an anomalous dissipation in turbulent fluids is something like this, or the way you should understand in general a cartoon picture of turbulence is that you have, say, a background flow which leaves at a certain scale. So for instance, you see whorls and eddies which are kind of moving at a certain scale. But if you then look more carefully and you sort of zoom in into this whorls, you're actually seeing another generation of things which are like, maybe smaller. And there is an interaction between the previous ones and the next ones. And this this interaction is kind of very non-trivial, right? And this picture actually keeps going on. I mean, like, you can then zoom into and you see sort of smaller and smaller eddies in your fluid. And of course, they don't have to be organized so nicely as in this picture, but eventually, at a certain point, if you have Navier-Stokes, if you have a viscous fluid, there will be a scale at which you will not find any interesting motion anymore because the viscosity is kind of regularized everything and sort of smoothing. Okay. Very well. So how it is now, these solutions in convex integration. So let me just put here a 2. Okay, so how are the solutions of this convex integration schemes actually organized? Well, VQ actually typically is in fact the sum for, say, I equal 1 to say some big scale, which I'm okay. So it's actually up to some Q, and you're actually going to have something which we call say WI. So it's organized in a series, and its WI have a typical length scale, which is very separated as I is actually varying. In fact, it's very separated in a way which, for technical reason, is going like a double exponential. So it's going down to 0 as a double exponential. But in fact, if it were not for just some technicalities, you could make them almost go down exponentially. So let me just say that at a scale, which I might actually call like, lambda to the minus I, roughly. Okay, so this is not precisely correct, because the real scale is really something like lambda to the minus okay, so to the minus b to the power I, but this b is very close to 1. So if we were maybe smarter mathematicians, we would be able really to actually set that b equal to, I mean, like we maybe would really be able to go down like a an exponential. Okay, and what is also the theory of turbulence telling you? The theory of turbulence is telling you that you're not expecting much interaction between, say, Wi plus 2 and all the summation until I. Okay, so Wi plus 2 should not interact with, say, the summation for j equal 1 to I of your Wj. And in fact, this is what is happening. And in fact, this is what is happening in these convex integration constructions too. So precisely what is happening in convex integration constructions. Okay, in fact, how would you, so what is really going on? So if you just call this guy, say, okay, so what is really going on? So what is going on is that if you consider VQ as this sum for I equal 1 to the to Q of Wi, and now actually VQ plus 1 is roughly going to be the previous sum plus a new correction. So let me call it WQ plus 1. What is in fact happening is that at first order, WQ plus 1 is essentially advected by the previous flow. And then if you look at the scale of WQ plus 1, there's going to be, of course, something in which the nonlinear interaction is happening. Okay. But I mean, for all purposes of the nonlinear interactions, what is really WQ plus 1 interacting with is WQ. And the previous ones are just like, flowing all of it as it should happen, but without really having anything more like substantial in the interaction with the addition that you're actually putting at step Q plus 1. Okay. And so let me just say over here, so WQ plus 1 looks a bit like a stationary flow or a stationary Euler flow, so some eddy advected by the background. VQ. And something interesting, something a bit more interesting than just this is happening with the previous frequency. Okay, very well. So now what is yet the theory of turbulence telling you? Well, the theory of turbulence is after this is actually telling you that there are certain scaling laws that you can actually derive on some statistical quantities. Okay, so there are some scaling laws that you can actually derive. And these scaling laws, for instance, are telling you that the energy, okay, so let me just call it like 4A. So the energy spectrum of your solution should behave roughly like a power law of the wave number. Okay, so this is the famous Kolmogorov five-third law. Okay. Then there is another conclusion for B, which is telling you that the correlation, so the second order structure function of the correlation of the velocity should obey like roughly like a third of the distance between the points that you're looking at. Okay, so this is the what is called the two-third law. Okay, and this two-third law is essentially telling you, or like, you know, in one way in which you could translate it, although this would be actually inappropriate, is that you expect your motion to be typically 1/3 Hölder in space. Okay, so that's not exactly it, because really what the two-thirds law is really telling you is that if you take a lot of turbulent flows, and if you compute for a good probability measure the expectation of the square of the difference of the velocities between 2 points. So if you compute this guy, okay, so this should roughly behave like modulus of x minus y to the power 2/3. Okay, with now something in front which I don't remember exactly, but so here over here somehow there is a constant in front which is depending on the say on the mean rate of dissipation. So on some, say, on something macroscopic. Some macroscopic quantity. Okay, let me not go into the details. And then there is actually a prediction, another prediction yet, which I want to draw your attention to, and that is that if, I mean, in the theory of turbulence of Kolmogorov, of course, viscosity is not absent, so there is viscosity, and you can compute what is called the Kolmogorov length, which is the length scale at which the viscosity should become important in your consideration, and you should like, you know, that length scale, that length scale is the scale at which this picture by Richardson, in which you have, like, you know, multiplication of eddies, stops being the correct picture, because at that place you at that length scale you actually have viscosity, which is kind of smoothing things out. Okay, So there is something which is called Kolmogorov length scale. And this is like essentially the length scale at which viscosity becomes prevalent. Okay, and again, this is something that you can actually like predict by simple scaling laws. And what is remarkable is that if you push the convex integration constructions, for instance, as it was done by Isett in the proof of the Onsager conjecture. So if you push it, until you actually get to the kind of threshold regularity of the Onsager conjecture, then in fact you can compute all of these quantities like the energy spectrum, like the typical Hölder regularity of your solution, or the Kolmogorov length scale for the convex integration solutions, and you would actually find exactly the predictions of the Kolmogorov theory of turbulence. Okay, so the say best, or if you want closest to critical, convex integration constructions match the predictions of the scaling laws. Okay, very well. So far I actually told you what is good. So what actually these guys are doing, but so the rest of my talk I actually want to focus on what they are not doing. So in which sense they are not going to be satisfactory, and what are the major drawbacks that you can actually see in them. So what is instead wrong? Okay. Let me just briefly mention, even though it's not going to be the focus of my my last 15 minutes, that, for instance, something like this, the fact that you have an energy spectrum, is almost correct, but not entirely correct. So what do I mean by this? Well, first of all, there is this technical fact, as I told you, that the frequencies are not, in these constructions, are not really going like a power, right? So still at the technical level, and this technical level is in a sense, when you actually go down and prove important, there must be a pretty good separation between the length scales of these eddies. I mean, like a much larger separation that you would actually like. So let's say, certainly you might conceive that you can actually push maybe this double exponential toward an exponential, but no way, for instance, this lambda is going to be any reasonable number, like 2 or 3. It's going to be like huge. So they're really far apart from each other. So there's not going to be a picture like this. This is the picture that you would like. Rather, the picture which is really going to be there is that the next eddies that you're seeing are exceedingly small and like, tiny. Okay. But most importantly, when you actually look at pretty much all the constructions, these building blocks over here, so these eddies, they live in very specific regions of the Fourier space. I mean, they are very far from being something which is like, sort of homogeneously spread among all frequencies in the frequency shell that you're looking at. So, and I would say this is like really very unsatisfactory from the point of view of what one is trying to describe, because what you would imagine is that in a chaotic motion, there's no reason why there should be only some particular frequencies which are actually excited and compared to others, even though they are living at the right space. Okay, so let me just put it over here as a remark. So first of all, maybe the Fourier picture seems wrong. Okay, so the next fact, which is not very nice, is that there is no error of time. I mean, when you actually look at the solutions, which are solutions of the Euler equation, they can as well dissipate the kinetic energy as they could increase the kinetic energy. So I don't think this is a dramatic problem. I mean, like if you're looking at the Euler equations are per se time reversible. So there's not really much that you can do. Of course, what you could do to remedy to this situation is just to put maybe some extra condition, like for instance, one condition that you could put is just to say the energy must be dissipated, and that would be similar to some, like what people in the theory of hyperbolic conservation laws do. They just put as an extra requirement for the solutions of your equations that there is an error of time because it's coming from some quantity, which might be the energy or the entropy. And that, of course, would sort of object to the fact that you can simply make a coordinate transformations in your equation and reverse time. So maybe not too problematic. Because you can enforce energy dissipation as an axiom. Okay, but what for me is really like the first thing which is very, very unsatisfactory of these solutions is that as far as we can see, somehow there is one big extra constraint that through viscosity has to satisfy. And the big extra constraint is that you have the energy conservation, which is what you already have actually at the level of okay, so let me just write it again for the Navier-Stokes equation. So for the Navier-Stokes equation, and let me write it in the following way, you have the energy conservation, which of course you have for these approximate solutions too. Okay, but what you are substituting now here in this energy identity, so you have this quantity over here, which is positive. And what is happening in the convex integration solution is that instead you have something like this. So this is something that I already wrote. Okay, so you have the divergence of, okay, say RQ times VQ. okay, which does not have actually such a nice structure as the Laplacian, but it's still something which is going to 0 because the derivative is taken outside. So this is going to 0. As this one here is going to 0 because there is this epsilon q. But this other term over here doesn't have a sign. So I don't know about that. So this term over here, which is going to be r circle q dot dvq, does not have any sign. Okay, and that's not actually very satisfactory. And so in the final part of the talk, let me, however, tell you that there are some progress into this question. So it is possible to devise schemes which sort of are dissipative in their nature. So from the start. Or if you want, of course, they are going to be dissipative in the end as a final like byproduct. They would actually produce weak solutions which are locally dissipative in the sense that so the limit would satisfy the following inequality in the sense of distribution, which is pointed out as an important requirement to come as a limit of solutions of Navier-Stokes in a paper by Duchamp and Robert. So they would satisfy this requirement, which like stands to reason that is a good entropy condition for solutions of the Euler equations. But there's actually more into it. They're actually dissipative also along the way. Let me just edit in the following. And by this, I just mean that it's dissipative along the way. It's a bit more complicated than this expression, but what is really going to be is that there's going to be like, you know, the divergence of some quantity. Okay, so dissipative along the way, which just really mean that I want some portion which is going to 0, which is the one that you have over here in the sense of distribution, and some portion which is not going to 0 in the sense of distribution, but that portion should have a definite sign everywhere. Okay, so it should be like everywhere bigger or equal than 0. Okay, and let me just give you now some results over here. So first of all, but this was done in a very ad hoc and a satisfactory way. So there was a theorem by Lászlo and myself, and this was back in 2008. And this theorem says, so there exists bounded let me call them locally dissipative solutions of the Euler equations. And so now here by locally dissipative, I really mean that this extra energy inequality holds. And of course, what is really like distinguishing it from usual solutions is that this energy inequality really holds with a strict sign. And so this was done, though, in a way which is kind of rather ad hoc, because there were some tricks to achieve this inequality over there. So in a sense, they are really not, they were, I mean, this thing over here was not really coming from a clean construction, which was dissipative along the way, right? So it's not really doing this thing over here, okay? But very interestingly, This was done for the first time by Isett. So in a recent paper. So his paper is really an iteration which is dissipative also at the approximate scale. And it's used it actually to prove that there exists Hölder solutions of the Euler equations which are locally dissipative. Okay, just for a funny, just as a funny remark, actually he calls them globally dissipative. I don't know why. I find it slightly misleading if you call it globally dissipative. So, but anyway, so let me just point this out for the people who maybe go there and look at the title of the paper. So he actually calls them globally dissipative. Okay, I guess there's an argument for calling them globally dissipative, meaning that it's really dissipative everywhere. But nonetheless, and he makes a conjecture, and the conjecture that he makes is that the threshold for the existence of these locally dissipative solutions should be the same as the threshold of Onsager. So the threshold Hölder regularity for their existence should be 1/3. But this exponent is kind of sufficiently far from this 1/3. It's a technical exponent. It's not too bad. If I remember correctly, it's like 1/19, 1/17. Anyway, this theorem, this conjecture seems actually pretty hard. And the best that we can do up to now is in a recent paper by myself and Hyunju Kwon, who is postdoc at the IIS. And so this was in 2020, last year. So in this paper, we get the threshold 1/7. And so this is the last thing that I actually wanted to tell you. And I hope you all join me in wishing happy birthday to Sasha.
Thank you very much, Camillo.
Okay. So I see there is a question. So what is locally dissipative? Yeah. Okay. Locally dissipative, I really mean that this energy inequality holds. So let me just answer that question pretty quickly. So locally dissipative means that this inequality holds in the sense of distributions. And you might notice that I'm talking about bounded solutions, or anyway continuous or Hölder solution. So I don't have any problem in defining somehow, for instance, the product of 3 components of the velocity. Okay.
I see that Sasha himself answered that it is
yes,
the divergence of the energy.
Yes, the divergence of the energy flux is negative. Yes, that's a perfect definition. Yes. Yeah. Well, there's the time derivative too. So and then the time derivative has a contribution to that too. But yeah.
Okay. So let me invite questions. So please unmute yourself and.
If you believe Kolmogorov's theory, then either and there's like a sequence of solutions which like dissipate the kinetic energy with that law, which as far as I know nobody can actually prove like rigorously. Here's the sequence which is doing that. I mean on a single time scale, I mean, right? So between 0 and 1. Well, then the limit is either not solving Euler, or if it is solving Euler, is solving Euler but with this kind of extra forcing which is coming from the viscosity. And so you can't really just say you completely want to rule them out, right? So for instance, if you want to capture that particular behavior, then there should be something like that.
Thank you. So other questions, please. Okay, let's thank Camillo again for a wonderful talk. Thank you.
Thank you.
And I hope to see everyone tomorrow. So remember, tomorrow is actually Sasha Schneiderman's birthday, and we'll have first two talks in the morning by Peter Sarnak and Simon Dyatlov, and then we'll have Sasha himself will be making some comments, and then we'll have the banquet. I see here yet one more note from Sasha in the chat. It is roughly that I don't know what is a weak solution of the Euler. That's the comment to your
for my
yeah, Sasha. Okay, and so see you everyone tomorrow. Thank you all. Bye.
Bye.